Alright everybody, welcome to review. Just going to have a little background music. This was the first song that I played in the first video that I made for this entire semester. So are you guys ready to party? What's wrong with a little feel-good music before we start studying? Math should be fun. You should have a good time. Alright, so let's stop all that. I just want to give you a little party music to get you guys ready and started for this review. We are cutting this review into 4 parts. First part being from 1 to 12. Second part being from 13 to 24. Third part from 25 to 36. And the last part will be from 37 to 48. Please make sure that you take a moment to try to watch all 4 videos. They will be available to you tomorrow, Thursday, January 12th. Alright, let's get started with the first question. First question says, sketch the graph of the piecewise function. We have x squared if x is less than 0, and the square root of x plus 1 if x is greater than or equal to 0. So the right hand side is our domain, and we did do this in Algebra 2. So that domain pretty much tells us in one area we will have an open circle, which is this one right here. And it's an open circle because there's no line underneath telling us to include the value. Here there's a line underneath, so this will be a closed circle at 0 because we're including the value. So now we're going to make a table. We will put 0 in the table because that's where our open circle will be. And we'll put it in this circle, this table, because that's where our closed circle will be. The values that we'll put here are values that are smaller than 0, so -1, -2. And values that are larger than 0 are 1 and 2. You don't need to put more than that. Alright, so now all we're going to do is just replace 0 in for x in the first equation. So we have 0 squared, which is 0. So at 0, 0, we're going to have an open circle. Next we have -1 squared, which is 1. And -2 squared, which is 4. So we have 3 points to plot. An open circle at 0, 0. At -1, 1, we'll just have a regular dot. And then at -2, 4, we'll just have a regular dot and connect the dots so it looks like half of a parabola. Because x squared is a quadratic function. It is your basic your basic function for your original for your quadratics. So you want to make sure that your picture looks like a quadratic. Alright, now for the next one, we have square root of x plus 1. So I replace 0 in here, plus 1. So square root of 0 plus 1 is equal to 1. So at 0, 1, I'll have a closed circle. Then I'll replace square root of 1, which is 1, plus 1 is 2. So at 1, 2, I'll have a regular dot. Now the next one is square root of 2. Now square root of 2, that does not give me a perfect square. So what I will do is change that value to 4 so I can have a perfect square to work with. So square root of 4 is 2, and 2 plus 1 is 3. So these points will be 0, 1, which is a closed circle, 1, 2, and 4, 3. And this is going to wind up looking like a parabola on its side. right, and that's pretty much it. That's all you have to do to plot this. Please make sure that you pay attention to what the domain restrictions are saying. These are domain restrictions. Because last year, a lot of students did make the whole graph and you don't want to do that. You want to stay within the limits of the domain restriction. All right, on to number 2. Okay, number 2 says which of the following functions is represented by the graph. So first thing I want to do is decide what the domain restriction is. I can tell that it's at 0. So I'm going to have something that's going to be greater than 0. That's on this side because it's to the right. And then this one on the left-hand side will be less than 0. Now, since they're both connected to 0, we don't know which one has the line, but it looks like all of the choices put the line with less than. All right. So now let's look at the less than equation. It goes down 1, right 1. Then it goes down 3, right 1. The only time you go down 1, right 1, and down 3, right 1 is in a quadratic. And since we're going down, it's a negative quadratic. So if you notice here, these are quadratics that are at -1, -1, and -2, -4. So that's the quadratic of just plain old negative x squared. All right, on this side, we're going up 1 over 1, up 1 over 1, up 1 over 1. That's just a plain old linear equation. So that means that this equation will just simply be x. So this is the equation of y equals x, and this is y equals negative x squared. So now we need to look at each of our choices to see. First choice says x squared. If x is less than 0, this is not a negative, so this one won't work. Next choice says negative x squared if x is less than 0, that works. And then x if x is greater than 0, that works. Oh, well, here we go. There's our answer. Okay, so when you have multiple choice, it's good to kind of like look at each choice and see if which choice works. Because sometimes when you do a multiple choice, we want to do our work first and then get the answer. But sometimes with multiple choice, it's good to look at our answers and see which of our answers matches our picture. So, you know, sometimes it's good to work backwards. All right, on to number 3. All right, type of discontinuity. There are 3 types. The first type is called jump discontinuity. It's basically when we have a point here and a point here, and it pretty much just jumps in the graph. It jumps from one point to the other, usually one closed and one open. And we have infinite discontinuity. That's usually an asymptote of some kind, whether it's horizontal or vertical. And it's an asymptote. It's going in both directions forever. And then the last one is called point. Or sometimes they call it removable. I don't know if I'm spelling that right, but removable or point. And that's when you have a graph and the whole graph is flowing, except there's just one little area, one little point where there's a hole. And that's called point discontinuity. All right, so we're going to look at each of these parts separately. So here at x equals -2, it looks like my graph starts here and then jumps to the next part of the graph. So it looks like x is equal to -2 has jump discontinuity. Okay, moving on to where x is equal to +2. If we look at the picture, it has a dotted line separating in between these two graphs. So that is what's called an asymptote. And since it's an asymptote going in both directions forever, this is infinite discontinuity. Okay, the last one is at x equals 4. And what it looks like in x equals 4 is that the graph flows, but just has one little point, one little hole that doesn't flow. So we call that point discontinuity. Okay, so the answer for number 3 is jump, infinite, and point. All right, number 4, which of the following is true about the function f of x equals x plus 4 over x minus 3? All right, well, let's see. The function is continuous for all real numbers. The function is continuous for all real numbers. And that pretty much is true. Not. Okay, it's not true. This type of graph, pretty much, it's a rational graph, and you're going to learn more about that next semester, but it looks like that. And it has like 2 asymptotes, which you'll also learn about next semester. Well, you actually did learn about it in Algebra 1, but the graph looks like this. It's not continuous because what happens is we're going, and then there's an infinite type of discontinuity, and then we're going in this direction. There's also a space somewhere in the graph where we'll have what's called a hole. And like I said, you'll learn more about this second semester. But, you know, for this question, you just needed to know about discontinuity, and we wanted to know where was it discontinuous. So it's not continuous for all real numbers. Now, we need to know where is that point of discontinuity, and you look at the denominator. The denominator can never be 0. We can never have 0 in the denominator. So we need to figure out what value for x will allow for us to have 0 in the denominator. So all you do is basically set this equal to 0. And we find out that at x equals 3, we will have a 0 in our denominator. Since that can never happen, this is going to be a hole. Well, since that's a hole, that's a point of discontinuity. So since that's a point of discontinuity, that means that the function is discontinuous at x equals 3. It is not discontinuous at x equals -4. Actually, at x equals -4, it's something else, which we will go into more in the second semester. All right. All right, determining whether something is even, odd, or neither all has to do with its symmetry, either to the x-axis or to the origin. So basically, if you are, oh, not x-axis, y-axis. So if you're symmetric, if your picture is symmetric to the y-axis, it's even. And if your picture is symmetric to the origin, it's odd. So an even function, basically the x value doesn't really change in the graph. So, well, I mean, it changes, but this is the formula for an even function, which means that whether you have a negative x or a positive x, the y value will stay the same. The y value will be positive. It's basically something that happens in like a quadratic. So in a quadratic, when you graph it, you know, if x is equal to -1, I mean 1 on this side, you'll still have the same value here at x equals -1. So that's what that means. So if your function is even, it's symmetric with the y-axis. That means it'll look the same. It'll have symmetry with this axis here. If your function is odd, it's symmetric with the origin. So basically what this is saying is that if you negate your x value, it's going to negate the y value. So when you have your picture, a cubic is a good example. Okay, if you have x equals 1 and y equals 1 here, chances are on this side, x equals -1 and y equals -1. So that's what happens with an odd function. All right, so looking at each of these, usually what you can do is just look at the highest power. That usually tells you whether something is odd or even. So that's the way I like to look at it. All right, so let's take a look at the first one. It's sine of x plus x cubed. Now there's really no way that we can actually look at this graph because we aren't allowed to use a calculator, but we should basically know what a sine graph looks like and whether it's going to be symmetric with the origin or whether it's going to be symmetric with the y-axis. So you know that a sine graph looks like this, and a cubic graph kind of looks like this. So if you add them together, they're going to both be eventually something that's going to wind up being symmetric to the origin. Because here this is 1 and this is -1. And the same idea here. So the first one is going to be odd. Okay, the next one is a quadratic. Okay, it's like a quadratic like this. So you can see right away that it is going to have that symmetry with the y-axis. Same things on both sides. Whether there's a negative x or a positive x, the y value stays the same. So the next one is going to be even. Okay, and the last one is cosine plus 4x. That means there's going to be something in it. Here's your cosine graph. And you know your 4x is a linear graph. So, you know, I'm not really sure how we would put them together on a graph. But this linear graph, it's not, because of this graph right here is neither even or odd. It's not symmetric with the y-axis, and it's not symmetric with the origin like these are. So this is going to be neither. Okay, these types of questions will probably be on the multiple choice. So just, you know, look at the picture. I mean, this is not the picture for C. I'm just guessing that because of the 4x, it's going to make it neither. All right, number 6. All right, which of the following statements is not true for x to the 2/3 power? With this problem, I actually made my own graph because I needed to see what the graph looked like so that I can see whether it was symmetric to the y-axis or symmetric to the origin or neither. So when I made my graph, when I made my table, if you remember from Algebra 2, x to the 2/3 is actually equal to the third root of x squared. So the x values that I chose were mostly perfect cubes so that I can get some values for my graph. So the first value that I picked was -1, because that is a cube, believe it or not. -1 times -1 times -1. And then 0, 1, and then I didn't go to 2 because I wanted a perfect cube, so I skipped right over to 8. Alright, and now we just plug it in. Cube root of -1 squared is going to be -1 squared, which is 1. Cube root of 0 is 0. Squared is 0. Cube root of 1 is 1. Squared is 1. And the cube root of 8 is 2. And 2 squared is 4. So then once I did that, I graphed it. I made myself a nice little graph so that I can, you know, pretty much have an idea of what this picture would look like. And, you know, I can even go as so far as to do -8 as well. And the cube root of -8 is -2. Squared is 4. So I just plotted it. Okay, so that's what the picture looked like. Okay, this is x to the 2/3 power. All right, first thing is the graph symmetric with the y-axis? Well, if I look here, here's the y-axis, and I basically have the same thing going on both sides, so yes, that is true. B, is this an even function? Well, even functions are symmetric with the y-axis, so yes, this is true. Is the range of this all real numbers? Well, range is how far low to how far high. Right now, my lowest point is at 0, and then on both sides, it winds up going all the way to infinity. So no, that's not right. And then the last one is what we call the right end behavior. REB, right end behavior. So on the right-hand side, the graph does wind up going to infinity. So this is correct. So the only thing that's not true, which is what we were looking for, is C. Okay. So because you don't get to have a calculator, sometimes you actually have to do some of these graphs by hand. So just make a table and it'll allow for you to see what the graph looks like. All right, on to number 7. All right, we're going to look at this function below. Right now we do have a point of discontinuity right here. So that means that we need to split this domain into 2 different domains. We're going to have a domain here, and we're going to have a domain here. Okay, our domain are all of our x values. So all the way to the left, right, all the way to left, all those x values. So the first set of x values starts at -6, and it goes around and stops right here at 1. So the first set goes from -6 to 1. Now it stopped here at -6, so that gets a bracket. But because of that open circle here, we don't know if it actually stopped there, so we put a parenthesis. Now in between, we're going to put a U. That U stands for union, and that means that we're basically just joining these 2 domains to make one graph. And we have to have 2 domains because of that hole. All right, the next domain starts back at 1 with a parenthesis, and then continues and stops here at 4. Okay, so there you go. There's your domain. And you only split the domain like this when you have a hole. If you don't have a hole, you don't usually have to split the domain. All right, the range of this is going to go from our lowest point to our highest point. The lowest point here really doesn't have anything to do, and the highest point have nothing to do with the hole, because regardless of this hole here at 1, we still are able to hit a high point and a low point. So we are going to be able to just write in our answers for the domain, for the range, as just simply being from -2 to 7. And because it never goes any lower than -2 and it doesn't go any higher than 7, we put brackets. All right, now on to number 8. All right, so for each function below, find a formula for f to the -1. This means inverse. Anytime you see the -1, it's an inverse. Even in trig, it's an inverse, okay? So inverse means to switch the x and the y, and then they're saying state any restrictions on the domain, which basically means after we do this, does anything affect our domain in our answer? Okay, do we have any holes? Do we have any points of discontinuity? That's when you would state any restrictions. So we shall see. Right now, this is f of x equals the square root of x plus 2. We're going to rewrite that as y equals the square root of x plus 2. First thing you want to do is switch the x and the y. Nothing else but the letters, the variables. Now the only way to get rid of a square root is to do the square And you're left with x squared equals y plus 2. Now, our goal is to get y by itself after we switch the x and the y. So we're going to subtract on both sides. And our final answer is x squared minus 2. Okay, we do have one restriction on the domain, and that's based off of the original problem. In the original problem, we can't have a negative for the square root. Like the square root in here can never be negative. And if you replace a number smaller than 0, you're most likely going to wind up getting some negatives. So the only restriction on our domain, because this picture here doesn't have a negative. So if you were to draw this picture, it would be here. It's not including this section here. So because it doesn't include this section, when you do the inverse, it's only going to wind up needing this section here. So we don't need any values on this side, although this graph would, we would be able to draw the whole graph. This original graph only takes up half. So when you do the inverse, it only is going to be half. So the restrictions that you have on the domain is that your domain can only go from 0 to infinity. Okay, so it can only go from here to infinity. That's the restriction on the domain. And that's only because the original picture did not, if there was a plus or minus here when we first started, then we would have no restrictions on the domain. But because it wasn't like that, we do have a restriction on the domain. Okay, and a restriction on the domain means, okay, when you look at the picture, is it going to encompass the entire x-axis or only part of it? So because it's only going to be looking at part of the x-axis, we do have a restriction on a domain. All right, this original picture is a cubic. If you know what a cubic looks like, it's like this. As you can see, no restrictions on the domain for the regular picture. So chances are when we do our inverse, we won't have any restrictions to the domain. All right, so the first thing you want to do is change your f of x to y. Then you want to switch the x and the y, only the variables, not anything else. And then solve for y by subtracting 4 on both sides. And now the only way of getting rid of a cube is to do the cube root. So we're going to do the cube root on this side and the cube root on this side. And our answer would be the cube root of x minus 4. And we have no restrictions on the domain. It's going to encompass the entire x-axis because of our original picture. All right. Number 9. Okay, it says the function g of x equals 5 times f of x minus 2 represents a vertical stretch of the graph of f of x by a factor of 5 followed by a vertical translation down 2 units. So you have to remember this formula. Okay, we did give you this earlier in the year. The A basically tells you whether you have a vertical stretch or a vertical shrink. You would have a stretch if A is greater than 1, and you have a shrink if A is a fraction, a number in between 0 and 1. Here, the B tells you whether you're going to have a horizontal stretch or a horizontal shrink. Okay, this is where it's kind of interesting because remember, things in the parentheses change. So since B is inside the parentheses, if B is greater than 1, it's a shrink. I know it sounds weird, but everything in the parentheses changes. It's the opposite. And it's a horizontal stretch if b is a fraction. Okay, so try to remember that. So if b is a fraction, it's a stretch, and if b is a whole number bigger than 1, it's a shrink. Okay, same thing with h, it's the opposite. This tells you whether you translate right, and that would be if you have a minus inside, or left, which would be a plus inside. And k, like a, will stay the same. So this tells you whether you translate up, that's if there's a plus, or down. That's if there's a minus. Okay, so A and K stay the same, and B and H are opposites. So it says that the 5 means a vertical stretch by a factor of 5, and that is correct. And then it says that we have a translation down 2 units, and that -2, that is exactly correct as well. So this is a true statement. All right, B says that 7 times f of x minus 4 represents a vertical and horizontal shrinking of the graph of f of x. So the 7 actually represents, because it's bigger than 1, a vertical stretch. The x over 4, since that is a fraction, and remember I told you fractions are opposite, that's a horizontal stretch. So this particular statement is incorrect. So this is a false statement. Okay, so make sure you have this written somewhere, because anytime they talk about translations, you want to, reference this. Okay, speaking of vertical stretch and horizontal stretch and shrink, that's what number 10 talks about. So remember, if you have a number on the outside, that is and it's bigger than 1, that's a vertical stretch. If the number's on the inside, it's opposite. This is a horizontal shrink. Since this is a fraction and it's on the inside of the parentheses, it's a horizontal stretch. Yes, I know, it's interesting, but it changes. And then the 1/3 on the outside means that we have a vertical shrink. So now looking at our choices, stretch horizontal, that is this one right here. Stretch vertical, that is this one right here. Shrink horizontal, that is this one right here. And shrink vertical, that is this one right here. Okay. All right, that's number 10. All right, number 11, which of the following represents the relationship between f of x and g of x? Remember, we did have a test on this a long time ago, in which we just gave you the graph, and then we told you what the translation was, and you had to change the graph based on that. So if you look at the first graph, this is f of x, and this is g of x. If you look at the first graph and you see basically how does it change, you see that this side goes down 2, and then this side winds up looking like it goes like up to 4, so up 2, and then it goes left 1. Okay, well, since this is going up to left 1, because based on this right here, and this just looks like it's going down 1, left 1. Okay, whatever happened, it still went left 1. So going left 1 means that it would be x plus 1 inside the parentheses. So it's that one. Okay, so none of the rest have x plus 1, but that's okay. We can just look to see what else this graph is doing. If we looked at our slope for the original graph, let's just say we just looked at our slope from here to here. It goes up 1 over 1. Up 1 over 1. You know, if we look on this side, up 1 over 1. So it looks like, you know, this side has a slope of 1, this side has a slope of 1. Now we look on this side, it goes up 2 over 1. Up 2 over 1. Okay, so this has a slope of 2 on this side. And here we go up 2 over 1. Up 2 over 1. Up 2 over. So this has a slope of 2 on this side. So since the slope, you know, multiplied by 2, we say that's a factor of 2. And since the slope increased by a factor of 2, that means it's a vertical stretch by a factor of 2. And the only thing that has a vertical stretch by a factor of 2 is this one. So it is number 11. So for questions like that, you have to look at everything that's going on. Like, how did it move? You know, it looks like it went down too, but it really didn't. It just did a vertical stretch. All right. Last but not least for this wonderful video is they want us to sketch the graph of the absolute value of f of x. Sketching the graph of an absolute value of a function means that we want to move all points below the x-axis to above the x-axis. So there's only 2 spots where we're below the x-axis. It's right here and right here. Okay, and I do remember giving a test on this. So all we want to do is basically reflect that line. So this little line here, we want to reflect it up above the x-axis. So we're just going to move this. And it looks like it goes down 1 over 1, down 1 over 1. So we're just going to now go up here. So we've eliminated this part. Okay. And then we're going to do the same thing here. It went down to -1, so we're just going to go up to +1. So that's our new graph. Okay, so if I want to like highlight the new graph, this is our new graph. Okay, so that orange peachy looking graph is the graph of y equals the absolute value of f of x. All right, everybody, that is part 1. Hopefully you enjoyed this. So look forward to part 2. All right.